Before we build the idea of limits and derivatives, I would like to discuss how is that we are going to use this, why is that we need it, so that you have a better perspective and a better appreciation for the topic. First thing first, I have a weird example. Say I have a circle. I want to fit the rectangle. So you can see the rectangle with the condition that we need to be having the maximum possible area. For example, this is a animation to show pretty much most of the possibilities that we can draw. So what you're looking at is we have a rectangle within a circle. It's fitting within the boundary of the circle. It's inscribed in the circle. And of course, as and when we change these values, the area changes. The area is not fixed. To show that variation, we have a area versus the height graph. So this is an expression which is expressed in terms of height actually. How is that we got this expression? It's simple Pythagoras theorem and length into breadth concept. So it's not too complicated, but anyways, we'll not go to that. So this particular function gives you guys the area that is bounded within this region and expressed in terms of the height. Here x is nothing but your height. So basically this length. Okay guys. So as and when we vary the height will also change. For different smallest values also we have the areas. Okay, so it's an approximation graph. But point is, where is the maximum area that is possible? Obviously the peak. This is the maximum area that is possible within this boundary. But of course, we can't do this and we can't plot the graph, and it's complicated actually. I mean, what I've done over here looks simple. But if you try to actually take each value and do it, you know graphs, right? Especially the graphs which are not straight. So such a graph, you can't keep drawing it. I mean, that's not make sense, is it not? So we can find this peak without actually going through all of this. Okay, next scenario. If I want to if I want to find the speed of an object which is under free fall at exactly 2 seconds. I'm not talking about average velocity, I'm talking about a velocity of an object at a particular instant of time, that is instantaneous speed. The word instant, you guys are familiar with that, right? Instant seems some food which is not healthy at all. But yeah, the word instant has to do with immediate. A web search, it's immediate, it's instantaneous. When you open your phone which is switched on and all of that, the response is instantaneous. That is within a very small duration you have the response. So instantaneous speed is nothing to do with the velocity of a particular or a speed of particular object at that particular point of time. Okay, so to figure out such a thing, we'll make use of derivatives and limits idea. One more which you guys can appreciate a lot more is to figure out and optimize, or how to optimize, the words have been repeated, how to optimize the design and performance of these complex machines such as rocket launching. So if I want to increase the efficiency of a rocket launch, I need to study about it. To study about it, well, I have this possibility. I can do this. I can plot all of this. So we are looking at 3 graphs. Rocket launch, let me put it in center for you guys. Oh, that's too big. Rocket's altitude versus time, rocket velocity versus time, fuel consumption versus time. That is, fuel is consumed, and as when you consume the fuel, your velocity will increase. So since it's been pushing, if the velocity is increasing means it's accelerating. It's accelerating means it's getting exerted some force on it other than gravitational force. Other than its weight, there is another force acting on it. And accordingly, how will the rocket move? What is the altitude to which it will reach? So this is a very simple version of rocket launch. Please don't take this seriously, but yeah. This is a start. Right? So I'm able to simulate this, I'm able to study this by understanding quite a few things, deriving a mathematical expression out of it. Okay, so all of this is against time. Okay, so I'm able to change the time and see how it behaves. So with this, I'll be able to talk about where should the payload actually exit the whole system, so that it takes a particular velocity and goes around the Earth or goes to the Moon or Mars or somewhere else. Right? All of this calculation is linked to your derivative. Okay, so there are of course a lot of scenarios. I'm able to just simplify a few of it. If you guys want to, yeah, please do make a running note, and yeah, by the end of it I'll be able to help you guys understand how to find this answer. It's a weird question, yes, but again, we are trying to understand the concept and build towards something which is more complex. Okay, so yeah, please make a small running note on all of this.